Good morning. So I want to finish up our discussion of Chapter 4 today. And in Chapter 4, we've really been discussing how reactions occur, or more specifically, how we think about how reactions occur, how we determine how reactions occur. We've talked about kinetics. Is a reaction first order? Is it second order? What's the rate determining step? And I want to continue this theme today and discuss two other techniques by which people determine how reactions occur, and also how we quantify effects on the rates of reactions. So what I want to talk about today are linear free energy relationships, relationships between substituents and their effect on the rate of reaction. And I want to discuss the kinetic isotope effect, the effect of isotopes on the rate of bond breaking in reactions. So we've been talking a lot about mechanisms that involve formation of carbocations, in part because I've wanted to give us sort of a limited subset of reactions to think about. And I want to return to a carbocation forming reaction, solvolysis reaction. And it's kind of similar to the one we were talking about before. I'm going to talk about substituents today. So I'm writing an X at sort of neither the meta nor the para position. We're going to see that basically as long as you put a substituent in the para or in the meta position, but not in the ortho position, it's all electronic effects that are going to influence what's happening at the reacting center. In other words, if we were to put something at the ortho position, there might be a steric effect. But if we have meta or para, we're able to separate it, and we're going to see the effects. We're able to separate the electronic effects. So the solvolysis, cleavage of the bond in solvent, bisolvent, in ethanol, of this alkyl chloride would give us the corresponding ethyl ether. And again, I'm going to draw our substituent X as sort of neither or either the meta or para position. And since it's a tertiary center, we know, as a matter of fact, from the types of studies that I'm going to talk about today, as well as kinetics, that this reaction is an SN1 mechanism. In sophomore chemistry, you would just learn this as fact. And today we're going to dig a little deeper and see how one understands, how one determines these mechanisms. So when I was talking about a similar reaction before, and I think I was talking about a secondary tosylate, I said, okay, we can talk about substituent effects, and we'll see a similar thing here. I said, okay, let's say we have X as the para-nitro group. The reaction's going to be slower. I'll say reaction slower than X equals H. In other words, having a substituent of a para-nitro group, an electron withdrawing group, destabilizes the carbocation and slows down the reaction. It raises the activation energy. We've discussed this qualitatively. If I have a substituent, if I say, let's say X is equal to paramethoxy, then the reaction's going to be faster. Then X is equal to H. All right, well, in 1937, Louis Hammett got this great idea. Let's make this a quantitative relationship and then use this quantitative relationship as a tool to probe reaction mechanisms. His idea was pretty simple. There are some things that are very easy to measure. It's very easy to measure pKa. If you do a titration, halfway in the titration, the pH is basically the pKa for an acid. So we can very accurately measure the pKa for a variety of benzoic acids, and therefore look at the effect of substituents. So the pKa of benzoic acid itself is 4.20. If we take paranitrobenzoic acid is substantially more acidic than benzoic acid. Its pKa is 3.42. I'll write more acidic. That kind of makes sense. You've got the nitro group pulling away electron density. You're forming the carboxylate. So you're stabilizing the carboxylate. If you think about the reaction, you're going ahead and favoring the product of dissociation. If we put on an electron donating substituent, a paramethoxy group, you get the opposite effect. Paramethoxy is funny because it's both electron withdrawing inductively and electron donating by resonance, but often it predominates as an electron donating effect. So the pKa is 4.47. It's less acidic. And I'll just I'm giving you deliberately sort of a limited subset of examples. I think that's one of the things that we're doing in this class is going into some advanced concepts, but taking a limited subset of examples to make things manageable. So, okay, one more example here. Let's take a metachloro group. The pKa is 3.83. So it's also more acidic, but not as acidic as a paranitro group. So Hammett's real innovation was to say, let's define some quantity for each substituent that can measure its effect, its ability to withdraw or donate electrons. And we'll call that that value sigma. So in other words, we can set up an equation here. Log K for an equilibrium over K naught is equal to rho, and I'm going to tell you about rho in just a second. But sigma here is a property of the substituent. So in other words, if we have an equation like the ionization of those acids, and I'll again write this sort of in generic terms with the X group going to either the meta or the para position, and we have the carboxylic acid plus H2O is in equilibrium. Equilibrium is K with the carboxylate and H3O plus, right? This is the definition of pKa. So if we say that we define rho as a property of the reaction, rho reaction, sigma substituent, and we say for this equation, by definition, let's make rho 1.0. In other words, we're going to say, let's use the ionization of acids, let's use the pKa of acids to now come up with a value sigma for every substituent that you can put on the acid. Let's come up with a value of sigma for a paranitro group. Let's come up with a value of sigma for a paramethoxy group. Let's come up with a value of sigma for a metachloro group and for lots and lots of others, and then see what we can correlate this with. One sec. And what we can correlate it with is pretty amazing, because for a whole bunch of different reactions, both equilibria and rate reactions, you see a linear relationship between sigma, now defined from the acidity of the acid, and the equilibrium constant, or the rate constant for the reaction. So in other words, we can write a parallel reaction for rates, log K over K naught. Oh, the naught, by the way, means K naught here is for benzoic acid, for unsubstituted. So in other words, K naught is for the substituent X equals hydrogen. And so for the rate equation, again, we can say the effect on some rate with a substituent, paramethoxy, paranitro, metachloro, etc., is going to be rho, some property of that reaction, times sigma, property of the substituent. And this very simple idea that once you define for substituents their effect on stabilizing or destabilizing, then for every equilibrium and for every process where you have a substituent on it, you can now say, okay, that reaction's going to have a certain perturbation of the substituent on the reaction, and the degree of perturbation is rho. There was a question over there.
I was just wondering if it was e to the sigma or e times sigma, but you just told me.
What? E?
Yeah, sorry.
Oh, rho. Yes, it is. The question was, is it e rho times sigma or rho to the sigma? Rho times sigma. Okay. Other questions? Yeah.
So I'm sorry, I'm a little bit confused of what exactly the rho and the sigma terms define and what they mean.
Okay, so in other words, you can now measure by simple acidity measurements. You can measure sigma for every substituent.
Are there any units for the sigma and the rho?
Nope, they are unitless. So K over K, and that makes sense because they're both factors, if you will. So this is, shall we say, rho is a property of the reaction that reflects the sensitivity to substitution. And sigma is the ability of the substituent to stabilize or destabilize charge. All right, give you an idea of this qualitatively. So we're looking here at a substituent that's right near the carboxylic acid. Imagine for a moment we had our substituent. You've heard of the inductive effect, right? Imagine for a moment now we have our substituent removed from the carboxylic acid. Well, when n equals 0, we've already said rho is equal to 1. In other words, it's going to have a big effect. Now imagine a limiting case. Imagine we had a very long chain separating the carboxylic acid from the benzene ring. What would rho be?
I guess 0?
Yeah, rho would, exactly. N equals, shall we say, infinity, or I'll just say it'd be 4 would be sufficient. I'll say greater than or equal to 4. Rho is about 0. And you can imagine now, let's say n equals 1. You've learned the inductive effect. If I have a single methylene here, I'd imagine the nitro compound would be an itsy bitsy bit, a little bit, more acidic than the hydrogen compound, but not that much. In other words, rho would be somewhere between n equals, between 0 and 1. So in other words, n equals 1, we could say rho is going to be less than 1, greater than 0. And that's kind of a quantification, and this really was Hammett's idea, to quantify this effect. So I'm about to erase these values here, which is fine, but you have them on your paper, and now I'm going to show you how Hammett determined sigma. All right, so what is sigma? And we're just going to determine from the pKa of each substituent. So in other words, for P nitro, we've already said that for the ionization of benzoic acid, rho is 1 by definition. We've defined it as 1. So for P nitro, 1.00 times sigma, right, ionization of benzoic acid. .00 times sigma equals log K divided by K naught. K naught is the equilibrium constant for the dissociation of benzoic acid, right? K naught, negative log of K is pK, like negative log of K naught is the pK of benzoic acid. So that's just going to be log of K naught minus log of K. Whoops, I'm sorry. I got ahead of myself here. Log K minus log K naught is equal to pKa. Whoops, what am I doing here? Equals pKa of benzoic acid minus the pKa of the, I'm just going to write it out, paranitrobenzoic acid. All right, so in other words, what Hammett could do is say, all right, for a paranitro group, we're going to measure the pKa, and thus determine that the sigma for a paranitro is equal to 4.20 minus 3.42 is equal to 0.78. And that's a fancy way of saying a paranitro group acidifies benzoic acid, increases the acidity of benzoic acid by 0.78 pKa units. And you can measure for all different sorts of substituents the effect on pKa. And table 4.1 in your book gives an extensive set of these measurements of sigma values for all sorts of different common substituents, both ortho and meta, on benzoic acid, both meta and para, rather, on benzoic acid. So I'm just going to transcribe a couple of numbers and tell you about them. So from table 4.1, on page 92 of your book, you can look up that for a nitro group, the sigma value for meta is 0.71. In other words, the nitro group is acidifying at the meta position, but not quite as acidifying as the para position, where it's in direct conjugation. And for a para substituent, the effect, as I wrote over there, is 0.78. The methoxy group is, methoxy is funny because methoxy is electron donating through resonance. In other words, the lone pairs on the methoxy conjugate with the pi electrons on the ring and push in electron density, so it's pi electron donating, but it's electronegative, and so through the sigma bond, it's pulling away electron density. So it's a little bit of a split personality. So a paramethoxy group is acidifying, a metamethoxy group is acidifying, but a paramethoxy group is deacidifying, negative 0.27 and negative 0.12. And by the time you move down a row in the periodic table, instead of being in the same row as carbon, you move down to chlorine or bromine. At that point, the pi overlap component of an electronegative atom isn't very good. They're not able to do much resonance. But the inductive effect, the electron withdrawing effect, is significant. So for chlorine, for example, it is electron withdrawing regardless, whether it's meta or para. The values are both positive. In other words, chlorine in the meta position or the para position makes benzoic acid more acidic. Yes?
Are these sigma values unique to benzoic acid?
No. So, okay, so now once you measure, and of course you don't only do it once, and it's been done, and it's in table 4.1. Once you measure that, the beauty of Hammett's idea, and this started as an idea, started to be an idea, oh, does this correlate with other effects? And the answer is yes. So when I said, okay, if you now for a benzene ring put a chain in the way, you will indeed now have that same linear relationship between the sigma values and the pKa. It's just that now with the chain, you'll have a smaller factor. Instead of a factor of 1.0, the rho factor, you'll have a factor of 0.5 or 0.3 or 0.1. And in fact, this is benzoic acid in water. Water's pretty good at stabilizing anions. If you do the same measurements in ethanol, which isn't as good at stabilizing anions, all the more weight falls on that substituent. So what do you think the rho value is for ionization of benzoic acid in ethanol? Is it bigger or smaller than 1? How many think bigger? Bigger. How many think smaller? All right. So why smaller?
Well, I would imagine ethanol is less capable of accepting hydrogen.
Ethanol is indeed less capable because it doesn't want to have ions in it quite as much.
Benzoic acid can't dissociate as
So benzoic acid can't dissociate as well. That is absolutely, everything is absolutely correct, except the conclusion, which now comes from a comparison. So why is rho actually bigger?
Because if rho is its sensitivity to substitution, I would assume that means it's a measure of how much it wants this particular substitution.
Uh-huh.
And like you said, if more weight falls on the substitution, it makes more sense for the number to increase.
Did people follow that? So basically, if there is more weight now on the substitution, then it has an all the bigger effect. So benzoic acid is indeed less acidic in ethanol, effectively a lower pKa. But now, if you put in a paramethoxy group, it really decreases the acidity because that anion now has just nothing going for it. And conversely, if you put in a paranitro group, it has a bigger effect because now that nitro group is the only friend in the world. Of course, I'm engaging in hyperbole, but it is the best friend in the world to that negative charge because you don't have a dielectric constant of 78, these huge dipole effects stabilizing the carboxylate. I forget what the dipole moment is of ethanol, probably about 30. You have a much smaller dipole effect stabilizing it. Okay, I hate to do this, but now I'm going to throw in one wrinkle here. I'm going to throw in one additional parameter. We're going to call it sigma plus. Sigma plus accounts for special resonance stabilization or destabilization of a carbocation. In other words, when we had the paramethoxy on the carboxylate here, you can't really push electrons to give a special stabilization of the negative charge. But when you have a carbocation over here, let's just come back to our sort of initial example. So you have a carbocation here, and you have a methoxy group like this. You can get a special stabilization of that carbocation just from the paramethoxy. So I'll say by a conjugated, which really means para substituent. So here we get this special resonance stabilization. We drew this out initially, I think in the first class we were discussing chapter 4, where we said, oh yeah, there's a special stabilization. I mean, this is special because here the carbocation doesn't have a complete octet. Over here in this other resonance structure, everyone has a complete octet. So if you accept that Hammett had to define one other special value, sigma for a methoxy group becomes now super stabilizing at negative 0.78 because it gets really extra stabilization. Other perturbations are much smaller. You can almost forget about them. So for a nitro group, instead of 0.78, it's 0.79. For a chloro group, instead of 0.23, it's 0.11. But really, it's a methoxy group where you have this humongous effect. All right, so the beauty of this is, and what Hammett found, was these relationships carry across reactions of all different sorts. So log K over K naught, whether it's equilibrium constant divided by equilibrium constant for hydrogen, or rate constant divided by rate constant for hydrogen, in many, many reactions where the mechanism doesn't change, has a linear relationship to sigma, and the value of rho, the slope in that linear relationship, shows the magnitude of stabilization. So let's take an example of a reaction here. And we've been playing around with solvolysis reactions, so I'll just take one I had some real numbers for. And I'm not going to give you, out of expediency, I'm not going to give you the raw numbers. I'm just going to give you a plot. And we're going to look at the solvolysis in ethanol. So it's the same basic reaction we've been looking at a lot, these SN1 reactions. And what I'm going to give you a sketch of is the graph of log of the rate constant K over K naught. And I'm going to plot that graph with various substituents. So I'm plotting sigma on the x-axis, log K over K naught, the rate constant of this reaction, the rate of solvolysis, divided by the rate of solvolysis of the hydrogen compound. And we'll plot this, and I'm just going to plot it. I'm not putting actual numbers here other than sigma values. So on my x-axis, I'm going to put 0, 0.37, and 0.78. You may notice that these are the values that we have for the metachloro, the paranitro group, and then I'll also put 0, of course, is hydrogen, and I'll also put I'll put a tick mark here at 0.37, but I'll put negative 0.78. And so on our graph, what I'm going to do is plot where the data points would fall. So negative 0.78 is our sigma plus for paramethoxy. And I'm just going to put a tick mark, a data point right here. And then let's see, I'll put a data point over here and a data point over here and a data point over here. And if I've drawn this correctly, I haven't quite gotten it on the line, which just shows how I do without a graph paper, without a grid here. But if I drew this correctly, what we get is a straight line. So here's our data point for paramethoxy, sigma plus. Here's our data point for hydrogen. Here's our data point for metachloro. And here's our data point for paranitro. And what one observes is a linear relationship. And if you think about that, that's kind of amazing that you can measure some simple pKa's for benzoic acid and then take another reaction, a completely different reaction, and see a linear relationship. Question?
With those numbers over there, the sigma para versus the sigma plus, since the sigma plus refers to a para position, do we just ignore the sigma para numbers?
Only for reactions where you are generating a reaction in. So the question was, do we ignore sigma para? And the answer is no. Normally you would use sigma para except for a special case where you have a carbocation in direct conjugation. So any other reaction, if it were ionization of, the N equals whatever, 1, 2, 3 case, you'd use sigma para. If it were formation of a carbocation but not in direct conjugation, you would use sigma para. It's just this special case. Other questions? Now, I haven't put any numbers on this graph. So you're going to have to trust me. A, this line is straight. Really, it's straight experimentally. In fact, what's cool is if you get a change in slope, if you don't get a straight line, which happens in some cases, that can reflect a change in mechanism of the reaction. The other thing that you're going to have to trust me on is that the slope, as measured for this, is negative 5.09. In other words, rho equals negative 5.09. And that's significant because the magnitude of the number is big and the slope is negative. So I'll say big magnitude and negative. And if you think about it, the fact that it's large makes sense because the relationship to the carbocation is incredibly intimate. It's more intimate than the relationship is to the anion here. It's closer, it's more involved, it's getting bigger stabilization, and boy, it needs that stabilization because it's not an 8-electron species. It's getting bigger stabilization or destabilization, so the magnitude is large. And the slope is negative. It's opposite the effect we had in stabilizing the negative charge. A nitro group is good in stabilizing the negative charge, but a nitro group is terrible for the positive charge. And so that's the significance. So large negative rho, so we say due to big effect of stabilizing carbocation or destabilizing. And this is a hallmark of SN1. In other words, if this reaction were SN2, you wouldn't have a huge effect. You might have a little effect of the substituent, but you're not building up much positive charge or much negative charge. You're not building up much charge. And as a result, the rho value would be very small. It would be much closer to 0. Maybe it'd be as big as 1, probably not, but it certainly wouldn't be negative 5 because it needs that stabilization of the intermediate. So if SN2, rho would be close to 0. And so just like kinetics, where we talked about unimolecular kinetics and bimolecular kinetics, the linear free energy relationships are a way to probe mechanism. Is a reaction SN1? Is it SN2? How much charge is building up in the transition state? Is it a lot? Is it a little? All right. So we've talked about linear free energy relationships. We've talked about kinetics. These are ways to probe how a reaction occurs. I want to talk about one other mechanism, and that is specifically the kinetic isotope effect. One other way, I should say, to probe. The effect of isotopes, and we're going to really talk deuterium versus hydrogen for this class. So I will simplify to say the effect of D versus H on rate of reaction. In practice, people can do it with C13 isotopes. They can do it with O18, etc. So let me again come back to something that I put up at the beginning of the class, a reaction that I put up at the beginning of a class. And I'm going to play on this reaction. It's another reaction I honestly don't know the mechanism for. So well, I know it's one of two. So specifically, imagine this tosylate. We started with a tosylate, and imagine we treat it with a base. So we started with a secondary benzylic tosylate. And that's right teetering in the middle. Tertiary's okay, often forming carbocations. Primary's really bad. Secondary's intermediate. Benzene is stabilizing. Conjugation is stabilizing. And so let's look at the elimination reaction to form a styrene. And if I want to balance my equations, which I only sometimes do, we'll continue to write plus the conjugate acid and tosylate anion. And so the question I want to ask is, what is the mechanism? Or more specifically, is it E1 or is it E2? And what we're going to look at here, and I'm not going to answer the question, I'm going to just show us setting it up, is there a primary kinetic isotope effect? And I'll explore the implications. And of course, I'm introducing a new term here. And we're going to explore what that term means. And we'll ask, so we'll parse this question with if we take the trideuteromethyl compound, the CD3 compound, right? Deuterium is just hydrogen with one more neutron. It's just a fat version of hydrogen. Is the trideuteromethyl compound much slower than the proteomethyl compound? And I don't have the answer for you, but that's something you could easily measure. You just set up a competition. You just put equal parts of the deuteromethyl compound and the proteomethyl compound in a flask, in some solvent with some base, and you let the reaction run, and you periodically measure the concentration of the styrene that has the deuteriums in it and the styrene that has the protons in it, and you calculate the rates for each, and you compare the two rate constants. All right, so if the mechanism is an E1, mechanism, then we would expect the mechanism to, remember, E1 is elimination unimolecular. E1 mechanism means in the rate determining step, you get formation of a carbocation. And so I'll write a curved arrow for this. You're going to be doing some curved arrow mechanisms on the homework. We haven't talked about different mechanisms, but you'll get practice in them. So we'll form a carbocation in the rate determining step. If I want to be a good person, I'm just going to write my positive charge. If I want to be a good person, I will also write tosylate anion. And then in a fast step, your base, whatever your base happens to be, maybe a bulky amine, or maybe hydroxide. Let's say hydroxide would be a good example. Your base, we'll just draw it as B, comes, pulls off a proton, and you get, in the fast step, and you get the corresponding styrene. And if I want to be a good person, I'll say BH plus. I suppose if it were hydroxide, it would be, the base would be OH minus, and the BH plus would be H2O. All right, so let's consider this reaction. And by now, we should be good at writing reaction potential energy diagrams, right? In a reaction free energy diagram, we write our free energy on the y-axis. We write our reaction coordinate. I'll abbreviate it as reaction coordinate on the x-axis. And we're going to sketch out the relative energies of the reactants, the intermediates, if there are any, and the products, and look at the transition states along the way. Okay, so the reaction is downhill in energy as we go from reactants, as we go from the tosylate in our base to the styrene and the other products of reaction. And in an E1 mechanism, we go through a carbocation. Carbocation is high in energy. We have two steps, so we have an energy hump to form the carbocation, then rate determining step, the highest energy barrier, and then we have a fast step down to the product. Now think about that. We're not going to have a big effect of the deuterium here. In this particular case, the deuterium's getting lost after the rate determining step. The slow step occurs, the deuterium is peripheral. It has very little effect. So the CD3 compound should have about the same rate. There's actually what's called a secondary kinetic isotope effect. It says it might be slightly different, but it should react at about the same rate as the proteocompound. In other words, the rate determining step, the deuterium isn't involved. So if you do this experiment, you set up a competition, and you see very little primary kinetic isotope effect, that's consistent with an SN1 mechanism. Now let's consider an SN2, an E1 mechanism. Now let's consider an E2 mechanism. All right, in an E2 mechanism, elimination by molecular, you just have one step. Your base comes along, pulls off the proton. You break the bond to the tosylate. At the same time, you get your double bond plus BH plus OTS minus. And now, we've talked about this before. You have a very different free energy diagram. You have your reaction coordinate. You have your free energy. You have your reactants, you have your products. But now you have no intermediate. Now, something very special about deuterium. CD bonds are stronger than CH bonds, but for a very special reason. So I'm going to write CD bond is stronger than CH. It is and it isn't. Let me show you what I mean. All right, imagine for a moment that we have a plot of energy versus the CH or CD bond. You get a curve. Those of you taking P-Chem have probably seen a curve that looks like this, right? You have your R-CH bond. You have an energy well. Seen a curve that looks like this? Maybe even in freshman chemistry. All right, and it probably goes deeper and steeper than I've drawn it. Okay, now you'll remember, if you've had P-Chem, that your energy is quantized. In other words, you are in a quantum oscillator, in a quantum harmonic oscillator, where even at the lowest energy state, even at the ground vibrational state, you have what's called 0-point energy. And the 0-point energy is lower for deuterium because of the reduced mass of a CD bond versus a CH bond. So the 0-point energy for CD than for CH. Put simply, you have the same energy curve, but due to quantum effects, due to the fact that it's a quantum mechanical harmonic oscillator, the CD bond sits lower in that well in energy. And as a result, when you're breaking the bond, you have to go ahead and put in a little more energy. And that energy translates to up to 8-fold in rate. So in this case, the deuterium compound should react much slower up to 8 times slower than the corresponding proton compound. And so the take-home message is, if you are breaking a CH bond in or before the rate-determining step, you have a primary kinetic isotope effect that's going to be close to 8. I'm going to write that. If you break CH bond in, I'll say, or before, by way of a pre-equilibrium, then you get a primary kinetic isotope effect of close to 8. And by close to 8, I mean, let's say 4 to 8. I'll say 4 to 8. A big effect on rate. If you break the bond after the rate determining step, then you have little or no effect on rate. And that's the take-home message I want you to take away. All right, we will pick up talking about Chapter 5 on Wednesday. We'll talk about molecular orbitals and paracyclic reactions.